So today we're talking about Coulomb's law, and I figured since I'm a physics major, I should probably put some videos with physics in them. I seem to have more of the mathematics videos right now, but I hope to bring both to the table in various subjects. So this is actually the first video in my playlist. Is going to be electromagnetism, which is my favorite subject in physics. So we're talking about Coulomb's law. Basically what it says is it describes the force between two charges, positive or negative, and basically what it's saying is the force is, let's see, where is there? Force is proportional to the product of the two charges, Q1 and Q2, and inversely proportional to the distance between them, or big R squared. Now when anything's proportional to something else, you can set it equal to that something else with a constant of proportionality k. Now, what's usually done is this distance between them is, since this force acts in a radial manner, this bottom term is usually 4 pi r squared, because that's the it acts over a surface of a sphere, and then this k turns out to be 1 over epsilon 0. That's just the proportionality constant that was determined, and they just bring it into the denominator, and that's 1 over 4 pi epsilon 0. That's the constant term. Now, epsilon 0 is called the permittivity of free space, and what that means is a permittivity is a measure of how well an electric field can develop inside a medium. And free space, or vacuum, is the medium in this case, and epsilon 0 describes how well that electric field can form inside free space. Now later on you get into material space, where each material has a different way that electric fields can form inside of them, and therefore epsilon 0 is not the correct term. You actually have epsilon r, and we'll get into that later. Basically, it's just a measure of how well electric fields can form in free space, is epsilon 0. So this is Coulomb's law right here. I'm gonna put a little box over it, and I should probably give the value of epsilon. Epsilon 0 is found to be 8.854 times 10 to the negative 12th farads per meter. So I'm just gonna do one of these things, farads per meter, and farads being the unit of capacitance. Units aren't terribly important. This constant of proportionalities usually have strange units because it has to equal force, the units on the right hand side. So okay, so we have this expression, and we're just going to develop it a little further here. This r squared is the distance between the two charges. So I drew a little something in paint. I hope that's coming in okay. Maybe I'll move it to like right here, so it's more in the middle. Okay, so alright, so this point right here is our origin. In fact, I'm gonna write that. Origin. That's the point right here of like a Cartesian coordinate system. And here's charge 1, charge 2, described with position vectors r1 and r2. Yes, they should have a little arrow on top of them, but hey, this is paint, and not very good in paint. But So we got this going on, and remember we said the big R, or R12, is the vector between the two charges. So the way to obtain that in vector form is, well, we're going to say that big R, and it's a vector, so I made it bold, R12 equals R2 minus R1, and that will give you this vector right here. Yeah, a little bit of vector analysis. Let's see here. Next in my note. So, alright. So force is typically a vector quantity. In fact, it is a vector quantity. So, and what we have here is a scalar. There's no sort of direction implied in this expression right here. So we want to write this as a vector. As a vector. No, not df. And I'm going to write this as a vector. So we have to use our vector notation. It has to be in the direction of R, of big R. So it has to be in the direction. So we're going to call it A sub R 1, not superscript, 1, 2. Because it's in the direction of R12 from this picture right here. So R1 A sub R12 though, what's that? That's gonna be vector R over the magnitude. Where's my little magnitude? There it is. Over nice bar over the vector R magnitude, and we can rewrite that as a lot of times we'll just rewrite this as just R like this, but I'm gonna keep it into magnitude form like that, just so it's consistent. So this is equal to R2 minus R1, and then divided by the magnitude of R2 minus R1. So that's our A sub R12. Now if we plug this into here, well, first we can replace this R right here by R2 minus R1, and then our A sub R can be replaced with this, like that. And then these denominators in the bottom are going to multiply together and give you a cubed, and that's going to go in the numerator. And here we go. This is the vector form of Coulomb's law. It can be written like this, or it can be written as we had before, where we just replaced R2, R1 with R1, 2. So like that, or it can be written like this. They're all equivalent. I don't want that F in there. All equivalent ways to write the same thing. So, as hopefully everyone knows, you have if you have two positive charges, they're going to repel each other. If you have opposite charges, they're going to attract each other. You got two negative charges, they're going to repel each other. So let's see what's next in my notes. Turn this page here. If we have more than two charges, because this equation just represents two charges, Q1, Q2. That's it. What if we have, I don't know, 7 charges, 20 charges? How do you describe that sort of behavior? And the thing is you have to pick a point of reference. A point of reference where you pick one charge you want to examine, and you find the force on that charge from all the other charges. and that force is going to be the quote-unquote superposition of all the forces from all the other charges. So basically, it's going to be F equals, I'm going to just copy this and replace some subscripts here. The charge we're interested in, we're just going to call it Q. So then this is going to be Q1, this is going to just be R, that's going to be R1, that'll be R, and then, so that's the first term, and then you have to add up this from the second charge,